All right, can everyone hear me? Perfect. Welcome to United Astronomy Clubs of New Jersey on this surprisingly rainy afternoon. Yeah, weather forecast said, maybe a little bit of drizzle at 7. Nope, entire downpour. With that, I think I see a couple people just getting out of their cars. And so to give them a little minute to come down here and get settled before the talk, welcome to people both here and joining us online, because that is right, we are live streaming this on YouTube and Twitch. So if you're ever on a really rainy day and just don't want to get out of the house and looking for something to do on a Saturday, you could join us here 8 p.m. online through a chat, which is very helpful. You could get to ask any questions, and we always get those answered at the question and answer session at the end. In addition, you could check out our website, uacnj.org. It's where you're going to find a list of all our upcoming talks, as well as lists of our member clubs and all the fun telescopes and scientific equipment we have going on. We also have our social media pages, our Facebook, our Instagram. We got a Discord channel where you can ask any question, get help with your telescope setups, or even just show off your astrophotography. We love to see the comments, and we love to reach out with and help you guys. So, for everyone here, we do need to do the safety briefing. If you need to use the restroom, that is the porta potty in the back. To my left, your right, it is illuminated by red, so as it does get darker, you'll be able to find your way there. In addition, we have a little museum and gift shop area, which I will be manning after the presentation and question and answer session, because still no way to be in two places at once. In addition, if it slows down and we get any amount of clear sky, I don't know, they might be able to open a telescope. If not, and it does stay rainy, unfortunately, we do like to keep our expensive telescope equipment protected, but someone might be able to at least open a telescope to show you what one of our rigs look like. I can't guarantee it. It does depend on who's here and who's available to open up a telescope. In addition, when we go to leave here, we are using our headlights. I don't like to get run over, and neither do you. I'm just going to assume no one likes getting run over. And even if you do, here is not the time and place to do that. And with any flashlights we may have, do keep those pointed to the ground, though, because even though we are using our headlights and we have no choice in the direction in which they point, we do have a choice with flashlights, and we don't need to unnecessarily blind people. With that, tonight's talk is about the James Webb Space Telescope and a look back on the 2 years it's been in service. This talk is given by Walt Windish. Walt has been interested in astronomy since he saw the Pleiades as a Boy Scout. He bought his first telescope in 1985, just in time to see Halley's Comet. Walt is a member of the North Jersey Astronomical Group and the Rockland Astronomy Club, and he's been volunteering at Jenny Jump for over 20 years. With that, here's Walt.
Thanks, Tim. Thank you. And thank you so much for coming out on such a beautiful day. You know, you must be professional astronomers. Can you turn it up any? I just had to run out and get new batteries. I think I'll try to talk a little louder. I'm a little thrown out here. So anyway, I brought my my 7-year-old grandson up here for the first time today, and it's a fitting initiation into astronomy to come up into the pouring rain. That kind of separates the astronomers from the couch potatoes. But yeah, on July 12th, 2022, we got the first images from the James Webb telescope, space telescope. And so the 2 years anniversary was just last week. And last year I did a 1-year update. This might be an annual thing. It's amazing all the stuff that comes out of the James Webb. And, you know, even just looking at 2 years, I really just had to pick and choose, maybe be a little arbitrary in what I pick because there's just so much out there. So my hope is that maybe some of you will feel incented to go onto the James Webb Space Telescope website, NASA's website, JPL, and just look at some of the stuff. And the pictures you'll see there, I've gotten all this off the web, so there's nothing top secret here. It's all taxpayer money. You and I paid for all this stuff. But if you go on the websites, you can see some real detail, amazing detail, much more than you're going to see from looking at this screen. So there we go. I can tone it down a little bit. Have you all heard of the James Webb Space Telescope? Yeah? Great. It launched Christmas of 2021, and we paid about $10 billion for it. So we better see some cool stuff for $10 billion bucks. It's a project between NASA, the European Space Agency, I'll refer to them as ESA from now on, and also the Canadian Space Agency. And as I said, the first images, there were 5 images released on July 12th of 2022. So we just celebrated the 2 years of images. This image here was just released last week on July 12th in honor of the 2nd anniversary. It's known to astronomers as ARP 142, but us common folk know it as the penguin and the egg. And what you're looking at are 2 galaxies interacting. And it might not look like it, but these galaxies have about the same mass. That little egg looks like it'd be a lot less.
When you don't have the mic up by your mouth, that's why they couldn't hear you.
No, I think you were shut off because they're hearing me good now. I'm just gonna, yeah. Okay. Okay, there we go. So today we're gonna look at some telescope history, but we're really gonna look at some images that have come out in the last 2 years and talk about why they're important to science. So these 2 galaxies have already done a loop around each other over about 100 million years, and we expect them to do a couple more loops over the next few 100 million years until they merge into one galaxy. And we'll see what that looks like. You know, when there's a lot of gravitational playing back and forth between these 2 bodies, and about 100 to 200 stars per year are being born in this 2 galaxies dancing around. Compare that to the Milky Way, where we've got about 6 or 7 stars being born every year. So it's quite a difference. Now we'll kick up our production when the Andromeda galaxy comes over and collides with us in about 4.5 billion years. But until then, we'll be cranking out the stars kind of slow. And if you look carefully, well, you have to look real carefully. There's 4 diffraction spikes here. In infrared, this is so bright that it actually causes diffraction spikes. And I'll show you what the source of those diffraction spikes are later. It's really a function of the telescope and not the object we're looking at. Let's talk about the telescopes for a couple minutes. The tube of the Hubble telescope on the right looks how we would imagine a telescope, right? It's got a tube, and it floats around in space. The light comes in here. It hits a primary mirror down here, which is reflected back to a secondary mirror, and then that's reflected back into the instruments. The Webb is much different. The Webb telescope doesn't have a tube. It has the same components. It's got a primary mirror, so the light comes here. It's focused onto the secondary, which is up here, and then it goes down into the instrument panel. When you see those diffraction spikes on bright stars, when it's a really bright object, these secondary mirror trusses are responsible for those spikes that you see in the pictures. And it only happens when it's a really bright object. So when you see something with spikes coming out of it, you say, wow, that's a pretty bright object for this. This is really meant to look at a lot of deep sky, very faint objects. But we do point it at some other fun stuff as well. Now the Hubble needs, since it doesn't have the Hubble has protection from the sun in the tube. This has protection in the sun, from the sun, in this heat shield, this sun shield down here. The James Webb telescope only works in the infrared, which we can't see. And infrared is very sensitive to heat. So we have to really shield it from the sun in order to get good images. The mirror is broken into 18 segments. It's about 25 square meters, almost 220 square feet. And it's made of beryllium plated with gold. And the gold weighs less than 2 ounces for something that huge. 270 square feet coated entirely by less than 2 ounces of gold. So it's a very, very thin coating. And the James Webb telescope has about 6¼ times more light gathering ability than the Hubble. And you see the Hubble's primary mirror next to the James Webb. Here's another huge difference. The Hubble orbits the Earth at about 355 miles, right? Compare that to the moon, that's about 250,000 miles away from us. So it's very close to the Earth. It was enough to fly up, it was close enough to take a space shuttle and fly the Hubble telescope up and deploy it. And we actually sent astronauts up there to fix it a couple times, service it, because it was so close. The space shuttle went up there 3-4 different times. Matter of fact, it was a joke because when it first went up, there was a problem with the optics, and it was close to unusable, and we had to send a space shuttle up there just to fix the optics, which is kind of embarrassing. I belong to this amateur telescope makers club up in Vermont, and we had one of the guys responsible for the Hubble come up and talk to us, and as he walked up to the podium, we had a big screen with Mr. Magoo on there, and believe me, he got an evening of abuse. But the Webb telescope is at a very cool spot called a Lagrange point, L2 to be precise. That's almost 1 million miles away from Earth. So the difference between 355 miles and almost 1 million miles is quite a difference. We had to send it up there by rocket. There will be no repair missions going up there as far as I know. And it's far enough away from the sun that it can use those shields very well to its advantage, and it's behind the Earth. And a Lagrange point is where every two-body system has an area where the gravity and the forces between the two bodies form like an eddy, almost like an eddy on a river, where there's no pull by either body. And that's the Lagrange point. And so each two-body system has 5 of these points. The James Webb is on L2, and he actually orbits that spot. In L1, just as a side note, has a very interesting instrument there called the Solar and Heliospheric Observatory, or SOHO. And what that does is it monitors the sun for coronal mass ejections and other things. Now, when we had that month or two ago, we had those northern lights that you could see all the way down Florida and beyond. That comes from a coronal mass ejection. So by having the SOHO at point L1, it gives us about a 20-minute warning, which isn't a whole lot, that something big is coming, if something big is coming. And it's no joke. Back in 2022, February of 2022, a coronal mass ejection caused a geomagnetic storm at the Earth, and the atmosphere expanded a bit. It expanded enough that some of the low orbit satellites saw a 50% increase in drag in their orbits. And we had a bunch of Starlink satellites up there. 49 were just deployed. We lost 40 of them. The orbits degraded, and they came burning up into the Earth's atmosphere. So that was about $100 million cost. And that wasn't even a really big one. The sunspot cycle peaks next year. It's 11-year cycles, but that's a whole nother talk. But it's kind of interesting. We've got stuff parked at a couple of these Lagrange points, and they're perfect for that. The only problem is that sometimes pieces of dust and meteorite also get caught in there, just like you would an eddy in a river. And we already had like a microparticle strike the mirror of the James Webb. No damage, but it was enough that we noticed it happened. One other thing I'd like to talk about before we get going is the electromagnetic spectrum. All the energy in the air around us, radio waves, your microwave ovens, the x-rays that your dentist or bone doctor uses, they all use electromagnetic energy. And that can be detected. We see that coming from the stars as well, coming from the universe. We only see this little piece right here. This is the visible light. Shorter wavelengths go to ultraviolet, X-ray, and gamma. Longer wavelengths, you got a big long stretch of infrared. Then you have microwave, and you have radio waves. And you'll see that the Hubble space was pretty much invisible. Most of the stuff you saw from Hubble was invisible light. There was some near infrared, and there was some ultraviolet, but mostly invisible light. The James Webb is all infrared, near infrared and mid infrared. And the great thing about infrared is that it cuts through dust. It looks for heat. So the stuff that's obscured from dust, but even gives out a little heat, can be seen by the James Webb scope. And as you can see, we pretty much have the entire spectrum covered, right up to the very large array of 21 radio telescopes in New Mexico separated, making a really large footprint. So we have most of the spectrum covered. But the James Webb is just in a class by itself, sitting out there at the Lagrange point 1 million miles away and taking infrared, having a great sun shield. It's a very, very special telescope. Here's a penguin and the egg again. And this is a visible light photo image from the Hubble. And this is infrared. It's slightly different than the one I showed you. The one I showed you before was the near and the mid infrared. This is near infrared only. But you can tell the difference here. You can see this dust lane, invisible, that the James Webb cuts right through. You don't even see that. You also see a little gap here between the penguin and the egg, whereas here you see this halo continue through this whole, it's a whole upside down U. You also see there are some areas here that just are outside of the scope's view, but you could see even around it, we're seeing a whole lot more as far as galaxies and just you're getting a whole lot more information in the infrared than you are from the visible. The visible certainly has its place. I mean, studying the structures of the dust clouds is important as well. But what I'm saying is that the infrared adds a whole new dimension. And a lot of the pictures you see will be infrared combined with visible, and maybe even some ultraviolet to give a better view. This is another side by side. We've got the Hubble image on top in visible light, and you've got the James Webb below. And this is just a stunning picture, especially if you see it in full resolution. This just gives you a hint of how magnificent that image is. It's an area called the cosmic cliffs of the Carina Nebula. And again, not only do we see the increase in the resolving power of a large mirror over the Hubble, you can see just how much more detail, but you also see how it cuts through those clouds and gives us a lot more detail behind there. We're seeing a whole lot more detail. We're seeing more stars. Just the picture is just so much fuller when you add the infrared image to it. And remember that scientists have to colorize these pictures. Infrared we can't see. Now, even the Hubble's not taking a picture like an Instamatic camera. Hubble's sending data back, and then there's an image processor that assigns the shortest wavelengths to blue all the way up to the longest wavelengths to red. And you get pictures that are visible light wavelengths, but they have to be translated from the data. Well, you have to do the same thing with the infrared, and they do the same process in most cases. They'll take the shortest wavelengths and color them blue all the way up to the longest wavelengths observed in red. But they're false colors. You'd never see that with your eye. But you've got to do something with it to see it. Sometimes they color it differently to bring out or accent different features that they're studying. So NASA administrator I like this quote. He says, "The promise of Webb is not what we know we'll discover. It's what we don't yet understand or can't yet fathom about our universe. I can't wait to see what it uncovers." And discoveries with any new technology, some of them you have an aha moment where you see something you've never seen before. But other discoveries take a lot of hard work by scientists, poring over the data for years before they come out and understand what it is they're looking at. And then other discoveries are just totally unexpected. Every time we learn something out there about the cosmology, we learn about 10 other things we know nothing about or we know very little about. And we also often have theories or our understanding of the universe turned upside down, but what we've discovered by higher quality instruments. So let's take a look at some of these discoveries. One of the main objectives for the Webb from the very beginning was to try to look back into time and see how early galaxies looked. We want to look at the formation of galaxies. What did they look like 12, 13 billion years ago, and how does it differ from now? So it's fitting that in July 22, when they first unfurled all of their equipment and the heat shields, they started looking for galaxies. Well, they had programmed which galaxies they were going to look at because they had some data from the Hubble that they used to figure out a lot of where they want to look. So they found what they thought was the oldest galaxy known to science, old by 100 million years. About 300 million years after the Big Bang was the estimate. So that's 13.5 billion years versus 13.8. So the reason we can do that is a telescope is like a time machine, bringing us back in history. So why would I say that? What do you think? Anyone? Well, when I look at something that's 5 billion light years away, that means that it took 5 billion years for that light to travel and hit the telescope. So I'm not seeing that object as it is today. If I were to standing right next to it, I'm seeing that object as it looked 5 billion years ago. So when we look at this object, and by redshift we figure out that it's about 13.5 billion light years away, that means we're looking at a galaxy, how it looked very shortly, 300 million years after the Big Bang, or what we estimate to be the Big Bang. So we're looking back in time. That's the amazing thing about telescopes. When something's X number of light years away, that's how far you're looking back in time. So this galaxy is known as Glass Z13. Glass is the catalog designation. Z13 is the redshift. The higher the number, the higher the redshift. The universe is expanding, and the further away things are, the faster they're moving away from us. And so their light spectrums are shifted to the red. Now, I'm not going to get too far into this, but the more the light is shifted to the red, the farther away they are. And we can measure that, and we can figure out about how old and how far away these galaxies are by looking at their redshift. So at the same time, scientists found another galaxy called Glass Z11, which is about the same age as the previous record holder, which was GN-Z11. Both of these new galaxies are rather small. They're about 1,600 light years across, and the other's 2,300 light years across. So they're small galaxies. Compare it to our Milky Way. Our Milky Way is about 100,000 light years across. The Andromeda galaxy is about 200,000 light years across. So those are some nice sized galaxies. These are pretty tiny. So the galaxies were discovered in early release data, but they weren't announced until the scientists had some time to really look at it, double check their measurements, and be sure of what they were saying. So here's another picture. The same image that we just looked at from the Webb camera is on the right, and that's the Hubble image on the left. And you know, keep in mind, when this Hubble image came out, this was clearer than anything we'd ever seen before that area. And now we're looking at the James Webb, and there's your diffraction spikes we were talking about. The amount of area that's covered in this picture in the sky is the same as if I took a book and held it at arm's length and looked at the period at the end of a sentence. The amount of sky that period covers is about how much area we're looking at here. And in the background, there's, you know, 1,500, 2,000 galaxies in this picture, in that little tiny speck in the sky. So here was a little surprise. The scientists continued to look at the data, double check it, and they determined later that the redshift of glass 13 was actually a little less, and renamed it glass 12. So it was 100 million light years closer than they originally thought. And they discovered that our Earth-based Subaru telescope, which is an amazing telescope up on Mount Haleakala in Hawaii, it has this adaptive optics where it sends laser beams and it can adjust its mirrors due to the Earth turbulence, the air turbulence. Just an amazing system. So apparently, a couple of months before Webb's first light, they discovered the oldest galaxy so far, and that's has a redshift of Z 13.27. So again, that gets us right back to the record breaker, but it was a different object, and it was one that was imaged on Earth and not from the Webb telescope. Glass Z12 is still an impressive find, but it shows you that scientists always have to be ready to subject their findings to more data. You know, sometimes on the internet, someone says, you know, trust the science as end of story. But that's really the most unscientific thing you can say, because scientists are always rechecking their hypotheses, their data, they're looking at new data, they're always ready to change their theory if the data requires it. Now, if you have a friend who tells you that the Earth is flat, maybe you could tell them to trust the science. I think that issue's been settled. But certainly, scientists are always checking their hypotheses, and instruments like the Webb telescope are really turning some of our theories upside down and sending us back to the drawing board as far as what's really going on. I love this image I got from the European Space Agency site. It shows the Hubble's optical image of a galaxy on the left, the Webb's infrared image on the right, and the combined image in the middle. So you've got three different images giving you three different sets of data in different ways. And again, the clarity over on the right is just amazing. This galaxy is known as M74. It's also known as the Phantom Galaxy because it's hard to see. But because it has an M number, we know that Charles Messier saw it back in the 18th century. So we've known about it. It's just very hard to see and got the nickname Phantom Galaxy. This is the, let me see. Yeah, this is the full image of the combined data. That's the Hubble and Webb data put together. That's a full frame image for you. It's just an example of how different observatories, when they're working at different wavelengths and working together, can give us a clearer understanding of something by combining their data. As ESA notes on their website, they said such a variety of galactic features is rare to see in a single image. The red colors mark dust threaded through the arms of the galaxy. Lighter oranges are areas of hotter dust. Young stars throughout the arms and the nuclear core are in blue. And older stars towards the galaxy center are shown in cyan and green. And we can also see, if you bubbles of star formation, bubbles of gas around a star being born. Just an amazing picture. And here's the infrared data from the James Webb all by itself of M74. Same galaxy we've been talking about. ESA notes that the addition of crystal clear Webb observations at longer wavelengths will allow astronomers to pinpoint star-forming regions in the galaxy, accurately measure the masses and ages of star clusters, and gain insights into the nature of the small grains of dust drifting in interstellar space. So these images add an awful lot to what scientists know about galaxy formation and star formation, and just the way that dust and other items move through a galaxy. And that blue eye in the middle kind of gives me the creeps. I saw that, it's like, whoa, thing's looking back at me. This galaxy is one of 19 nearby face-on galaxies that have been selected and to be charted and studied by the Webb team. Hubble gave us the data that we used to select which ones we were going to focus on to start with, and we picked 19 of them. There's 19 of them. The project is known as the Physics at High Angular Resolution in Nearby Galaxies program, or FANGS for short. So if you Google FANGS project, you will either get this or you'll get a vampire, one of the two. It'll be in some interesting pictures either way. But there's a picture of all 19 of them. Early images of 19 face-on spirals from JWST in both near and mid-infrared. So between the James Webb images and those of Hubble and the European Space Observatory, researchers can now study these galaxies in ultraviolet, visible, infrared, and radio light. We can study them across the entire spectrum. Amazing. And each spectrum offers up different secrets of the galaxies that we're looking at here. According to Janice Lee, a project scientist at the Space Telescope Institute, these new images are mind-blowing even for researchers who have studied these same galaxies for decades. Bubbles and filaments are resolved down to the smallest scales ever observed and tell a story about the formation cycle, about the star formation cycle. Don't miss that phrase, even people who have studied these for decades. So there's scientists that have been studying galaxies, these galaxies, for decades. That's a lot of long, hard work to come up with what we know. It's not just, oh, nice picture, oh, look at this, we're done. These scientists have been studying for decades. There's millions of stars in these images. The Webb's NIRCam, which is the near infrared, that's the closest to the visible light, captured millions of stars in these images. And the older ones are shown in blue, clustered around the center of the galaxies. So you see the blue ones are the older ones. In visible light, usually the blue ones are the new ones. When you see two galaxies colliding and you see a whole bunch of blue stars, they're usually the newly formed hot stars, the hot young stars that die quickly, the James Dean stars, right? They die young because they live wildly. Webb's secondary instrument, the MIRI, which is the mid-infrared instrument, that's the infrared that's a little further away from visible light, is responsible for imaging the bright glowing dust, which appears in red and orange between and around the stars. And the deeper red shows gas-encased protostars. So one of the first for JWST is the amazing detail of large spherical gas shells and dust. Another detail worth noting is that the larger images of these galaxies, you can see pink and red diffraction spikes, which is a clear indication that there's an active supermassive black hole at the center. Or a very large star cluster. And diffraction spikes again are indication of what? It's showing brightness, right? And in this case, not visible brightness, but infrared brightness, which is heat. So they're showing intense heat if you're going to see diffraction spikes in the James Webb Telescope. And in the middle of a galaxy, that's a clear indication of a supermassive black hole gobbling up a lot of other matter or a very intense star cluster. About 200 million light years away is Stephan's quintet. It's a fun object for amateur astronomers to try to find. And when amateur astronomers, your eye is like a shutter speed of about 1/30 of a second, if anyone's into photography. You're never going to see any color when you're looking at galaxies. You're going to see fuzzy patches of what looks like a cloud. So don't be disappointed if you come on a clear day and you look up at a galaxy and it's just milky white. You're never going to see that kind of color. You have to have some kind of instrument, some kind of even invisible light that can gather light for quite a long time. And with the digital age, astronomers can, even here, amateur astronomers can take photos. They can take 100 one-minute photos and then stack them on top of each other and gather the light that way. When I started out in the film days, I'm a real old geezer, I would have to take 40-minute exposures and guide on a guide star to make sure that my telescope wasn't moving too much to get a blurred image. And it was really a masochistic endeavor. Now it's so much easier. The stuff you can get with telescopes today, because you take a lot of short exposures that don't require a lot of tracking, and then you just use up the software and stack them up on top of each other, and all of a sudden you got an amazing picture. It's so much easier these days. So anyway, if you look at Stephan's quintet, if you find it, you will just see a lot of milky white. But this is a group of 5 galaxies located in the constellation Pegasus. And the Hubble image, which is on the left, let me just the Hubble image on the left and the Webb is on the right. The quintet is notable for being the first compact galaxy group ever discovered. And that happened in 1877 by French astronomer Edouard Stephan. It's also a favorite object for more advanced amateurs to look for because it is kind of hard to find, but when you see it, it's like, wow, I did it, finally. But its real claim to fame is it made an appearance on that Christmas classic, It's a Wonderful Life. I don't know if anyone sees that, but there's a picture of Stephan's quintet up there when they're talking about the angel. They look up to heaven, and there's Stephan's quintet in black and white. The image covers about 1/5 of the area of the moon, so it's a pretty extended object as far as deep sky objects go. That's enormous for a space telescope, and in order to get a image like this, they had to put together 1,000 image files and make a mosaic just to put that together. So again, there's software called stitching software, and so they used stitching software to put the mosaic together of all those images. And once again, we see details never before seen. Millions of young stars and regions of fresh star birth with tails of dust created by galactic interactions, including a shock wave shown in red and gold at one galaxy, NGC 731. So this was, imagers used red and gold to show this shock wave separate from the gravitational interactions. And so those two galaxies are coming together. Again, they're all false colors, but sometimes we change from the regular formula to something else just so we can show something specific like that shock wave. The MIRI, which is the mid-infrared, sees a distinct difference in color between dust in the galaxies and the shock waves between the interacting galaxies. And so the image processors took all the MIRI data and colored it yellow and orange. And then they assigned blue and white colors to the near-infrared cams data to show the stars. And so we took, again, 2 sets of data and put it together to come up with this image. The leftmost galaxy, right here, NGC 7320, is only positionally part of the group. It's kind of like a galactic photobomber. It's not really gravitationally attracted to the others. It's well in the foreground. It's 40 million light years from us. All 4 of the others are connected gravitationally, and they're about 290 million light years away. So they're 250 million light years further away than that one photobomber galaxy. So it's a great group, at least the quartet, to study galactic interactions. These interactions are critical to all galaxy formation, and we learn a lot from that. Scientists rarely get such a good view of how these interactions trigger star formation. And as a bonus, there's thousands of galaxies in the background of this picture to be studied. Okay, we're going to shift gears, and we're going to leave the galactic and come back to our solar system. Anyone know what this is? Exactly, I heard it. So this is a side-by-side Hubble image of Uranus. On the left was taken in 2022, and the Webb photo just taken a year later in 2023. That's on the right. Look at all the extra detail and the extra number of rings that we see with the Webb telescope. The Webb photo gives us amazing detail of 11 of the 13 icy rings around Uranus. Only Voyager 2 spacecraft, which actually flew by in 1986, and the Earth-based Keck Telescope Observatory imaged the faintest rings. But this image is still amazing. And remember, since it's taken in infrared, the colors have been added. We also get a nice view in this of its polar cap. It's kind of hard. It's not a very contrasty image here up on the screen. But you can see the polar cap to the right, and there's even a brighter white spot there. It takes Uranus 82 years to orbit the sun, so each hemisphere of Uranus experiences a winter lasting 20.5 years. So that's a lot of shoveling. NASA notes that on the right side of the planet there's an area of brightening at the pole facing the sun known as the polar cap. And that polar cap is unique to Uranus. It seems to appear when the pole enters direct sunlight in the summer and disappears in the fall. And Webb data will help scientists understand this phenomenon because right now it's a mysterious mechanism to them. So it's another mystery. See how I'm doing on time. Okay. There's another picture. So Webb took this great wide-angle view. To me, it doesn't even look real. And of course, the letters were all added. They weren't floating out there. But I mean, when you look at the planet and 6 of its known 27 moons, it's just amazing. It just doesn't. To me, it doesn't look real. It almost looks like a drawing. This was a NASA release from February of 2023, and this image came from a single 12-minute exposure, which is also amazing. This isn't a stacked image like so many of them are. They pointed it at that part of the sky, took a 12-minute exposure, and that's what they came out with. Notice that all the photos that I've showed you shows Uranus's rings horizontally, not vertically, and not horizontally like all the other planets. And that's to remind us that they are 100. That they are vertical. There's a 100-degree tilt to Uranus. It spins on its side. I guess the current theory is that an Earth-sized object hit this planet way back when and knocked it on its side. We'll see if data will ever prove that, whether we're right or wrong. But it is on its side. Its rings are up and down just like that, where all of the other rings, Saturn, Jupiter, Neptune, they're all horizontally situated. So this orientation means that the planet's poles experience many years of constant sunlight, followed by an equal number of constant darkness. That I just put that chart up just to remind us of where the planets are in the solar system: Mercury, Venus, Earth with its moon, Mars, then you got the asteroid belt, Jupiter, Saturn, Uranus, Neptune, and Pluto. I never forget Pluto. It's still a planet in my heart. But Jupiter, Saturn, Uranus, and Neptune all have rings. We've known about Saturn's rings since Galileo discovered them with his small 20-power telescope, although he thought they were handles or a really big moon. He wasn't sure what they were, but he saw bulges that he thought were something else. But it wasn't until the 1970s that we discovered rings on any of the other planets. The rings around Uranus were discovered in 1977 using the Kuiper Airborne Observatory. So they were up in the air taking photographs when they discovered those rings. Jupiter's rings were discovered 1979 when we flew a spacecraft by, Voyager 1. That's when we discovered those rings. And the rings around Jupiter weren't discovered until 1989 when Voyager 2 flew by. So two of the planets, we didn't know they had rings until we flew really close to them and took pictures of them. So let's head a little closer to Earth. We're going to skip over Saturn and look at what James Webb has told us or shown us about Jupiter. Jupiter is an amazing planet, as they all are. Scientists have been studying the clouds on Jupiter for a long, long time, and its thick atmosphere is full of surprises. And by combining images taken at different wavelengths, we can see different layers of Jupiter's atmosphere at the same time. And using data from Webb's telescope in the infrared, they discovered a jet stream along the equatorial cloud belt of Jupiter. And this area, I don't know if you can see it, but this box, this is where they've seen the jet stream. And they've taken this box and put it up here, and these little boxes are areas where they have been able to detect wind shear, which gives them the idea that we've got a jet stream and we've got winds moving at different directions or at different speeds, which is just amazing. I mean, can you imagine studying? Of course, it's a more detailed, but can you imagine studying this and coming up with wind shear? Now that I've told that there's wind shear, the only thing I can see that shows to my untrained eye is this. You see how this looks like a wave? We have clouds like that on Earth. They're called Kelvin-Helmholtz clouds, and they're really cool. I've only seen them once. They look like a band of ocean waves in a row, and it happens when two layers of the atmosphere are moving at different directions, and so the top makes it look like it's a wave curling that you could almost surf. And so when I looked at this data, that little curve of a wave there is the only indication that I had of what the experts see in all these pictures. But they see wind shear in all of these pictures, and a jet stream. So here's an amazing picture of Jupiter taken by Hubble, and I only show this to you because the next thing I'm going to talk about is the giant red spot that's been there at least 150, 300 years, maybe more. And it's a giant storm. It's known as an anti-cyclone. And the reason why it's an anti-cyclone, cyclones and hurricanes happen with severe low pressure systems, right? When a hurricane comes by, the pressure goes right through the floor. An anti-cyclone is a high pressure system that turns around. So it's like a hurricane, but it's made of high pressure instead of low pressure. This red spot is 1.3 times the size of Earth. Keep in mind, 11 Earths can fit across Jupiter. 1,300 Earths can fit inside Jupiter. So it's just an amazingly large planet. And although Webb really is aimed to explore the outer reaches of the universe, it has given us some really new information on our own solar system, including Jupiter. So last month, June 26th, so not even a month ago, astronomers announced that they found previously unseen structures and activities in the atmosphere above Jupiter's Great Red Spot. So the current theory is that these strange occurrences are caused by powerful atmospheric gravity waves, which I have no understanding of. But that's the current theory. And so we see in infrared, obviously this looks a lot bit different than the visible light picture we just saw. But here's the red spot in infrared. They've rotated this about 90 degrees, and this is the area that they're talking about. And they're seeing some pretty interesting activity. And even though the Great Red Spot winds range between 270 and 420 miles per hour, astronomers thought the space above the red spot may have been boring. I don't know why, but they didn't think it was worth a lot of time studying until this image came up. So the Webb has proved them wrong and given them a new mystery to figure out. And you know, Jupiter never ceases to surprise. Neither does the JWST, for that matter. So while we're on the subject of planets, does anyone know what an exoplanet is? All right. Exoplanet is a planet that's outside our solar system. And another major goal of the James Webb Space Telescope is to discover exoplanets. So astronomers have found thousands of exoplanets since the first one was discovered in 1992. Most were too far away or too close to the sun to directly image. It's kind of tricky imaging an exoplanet in the glare of the sun, and if it's too far away from the sun, then there's not enough light to image it. So they're very tricky to direct image. But in September of 2022, NASA released these 4 images on the bottom. It's an exoplanet orbiting the star HIP 65426. And they named the exoplanet by just putting a B after the star's catalog number. And the background photo shows the star, and you see the diffraction spikes. And the bottom pictures, you see a little star image. That's where the star is masked. They use a mask called a coronagraph to cover the star so it doesn't get a glare to it. But it's a Jupiter-sized planet orbiting the star. We discovered it in 2017, and we are able to photograph it a few years later. These images are seen through 4 different filters. The 2 images on the left are in the near infrared, and the 2 on the right are in the mid-infrared. And the Webb's powerful infrared instruments just capture this in an amazing manner. This huge planet is orbiting around its sun at about 100 times the different distance of Earth from our sun, over 9 billion miles away. So you could see, that's why you could actually see a space between where the star is and the planet, even at the distance that we're photographing at, because it's 9 billion miles separation. That's 3 times the distance of Jupiter. So it's out there, and it may be the reason why we were able to successfully photograph it. So the real teaser is pointing the way to future observations of exoplanets. NASA's web page tells us that one of the main uses of the James Webb Telescope is to study the atmospheres of exoplanets, to search for the building blocks of life elsewhere in the universe. And this is an artist's drawing of data that we got from JWST. We found a planet that astronomers have named K2-18. So it's not an actual image, it's just what we feel it may look like based on the data. This planet is about twice the size of Earth, and it orbits a star at a distance that astronomers call the habitable zone. The habitable zone. I call it the Goldilocks zone, right? It's just right. It's not too close to the star. It's not too far away. It's just right to give life a chance. And it's about 120 light years away from us. And we think that this planet could be just an ocean of water with no land, just a big ball of water. They've detected carbon dioxide and methane in the atmosphere without detecting ammonia, which is a good thing. It indicates that there's likely water under a hydrogen-rich atmosphere, which we have a hydrogen-rich atmosphere with water underneath. Thankfully, we have a little rock that we can climb up to now and then, but that's the way you can describe Earth, except with the addition of land. So they call this a Hycean planet. It's the combination of hydrogen and ocean, Hycean planet. It's hydrogen and ocean put together. On January 31st of this year, NASA announced the discovery of exoplanet TOI 715b. It's 137 light years away from us, which is pretty close to us, considering the Milky Way is 100,000 light years across. 137 light years doesn't look all that far, unless you want to get in your car and drive there. The planet has about the mass of 3 times of the Earth, so it's about 3 times bigger than us. And it's another planet that's in that Goldilocks zone. It may be habitable. And the other thing is it's a rocky planet like Earth, which is even more hopeful for life. So the search for exoplanets is very exciting. Every time one is discovered, we discover a whole new world, and we have a whole new mystery of figuring out what exactly that planet is. Can it support life? And just figuring out the story. So I hope some of you will be interested enough to Google some astronomy sites and check that stuff out. So I'm going to leave you with one mystery. I'll leave you with one mystery that we have not solved yet, that we'll see how the James Webb does, and that's the small matter of the end of the universe. How will the universe end? We used to think that this galaxy was the universe and that it was static. It never changed. It was eternal. Matter of fact, Einstein put a constant in his theory of his relativity equations to make the universe constant, because he didn't like the fact that it looked like it was expanding, and that implied a beginning to it. But we used to think the leading theory used to be the Big Crunch, that the universe would expand, slow down, and then reverse the Big Bang and just crunch together, and maybe even rebound and do that a couple times. That was the leading theory. The leading theory now is the Big Freeze. And the discovery of dark energy changed everything. When we found out that the universe was not only expanding, but the expansion was accelerating, and we didn't really understand what dark energy was, and we still don't, we came to the conclusion that probably we're going to just keep expanding until everything dies out. Everything, entropy takes over, mass is equally distributed, and the universe will be a couple smidgens above 0 degrees, absolute zero. If dark energy continues to push the expansion rate of the universe into infinity, we'll end up with the Big Rip, which means that everything, including atoms, get torn apart as they speed up, and approach the speed of light. So the most likely scenario is the Big Freeze. In a Google years from now, if it's the Big Freeze, Google is 1 followed by 100 zeros, and that's where Google got its name. The last supermassive black holes will have evaporated, and the universe will enter the dark era, where matter no longer exists. So we started with a big bang, and scientists think we'll end with a little whimper. And on that cheerful note, thank you very much for coming out and spending some time with us.
All right. Thank you, Walt, for another great talk. Thank you guys for joining us. So, we will be doing a question and answer session because I'm sure you have questions that you want to grill Walt with. If you don't, I'm sure the crickets will keep going. But I do know the online people have some questions. But before then, I noticed a couple of you snuck in after the safety briefing, and that is unacceptable. Safety briefing. If you need to use the restroom, that is the porta potty in the back. It is illuminated by red. We also have a little museum and gift shop area that I will be manning after the question and answer session. Unfortunately, we looked at the radar. The skies are not going to clear, so be that as it may, I believe no one has opened any telescopes today. When we do go to leave here, we are using our headlights. Let's not run anyone over. It's wet and damp, and that just causes paperwork that we then have to sit here and do in the wet and damp, and that's just not a fun time. So let's avoid that. When we are walking, if we have flashlights, do keep them pointed at the ground, though, because we can control the direction of our flashlights, even when we cannot control the directions of our headlights. With that, for the people here, question and answer session works as follows. Assume I am a T-Rex. My vision is based on motion. So you will raise your hand and just wave it about like you just don't care. And you will keep it up until I get to you with the microphone. Because when you put your hand down, you kind of disappear into the forms in the void that is the dark. Since I forgot my distance glasses at home. Online people, you have it easy. Just type it. So, the first online question. Besides the fact that a tube would be unwieldy to have for a mirror that of James Webb size, why did they choose a tubeless design?
Well, they were sending this out 1,000,000 miles. And so you got to strip it down to exactly what you need. And a tube around a mirror that big would add an awful lot of weight to it. And it was just impractical. You know, even astronomers, amateur astronomers, you'll see Dobsonian telescopes which stand this high, and instead of having a solid tube, they'll just have some trusses holding it up because it's just not necessary as long as people don't shine their flashlights around.
As long as you don't have those jokesters who want to really mess with your
White
images.
light,
But
that sun shield, remember the sun shield
UFOs randomly going by. Ha ha ha! We turned our headlights on.
Remember that sun shield is the size of a tennis court, and it goes around with the Earth, around the sun, and it always has its back to the sun. So it does a really good job of shielding out. We're lucky it deployed. When the James Webb telescope deployed, there were over 200 single points of failure that were possible that crushed the mission. It was 10 would make me nervous. 200, and a lot of them were the pulleys that were part of that shield. If one of those pulleys failed as we were unraveling that sun shield, the sun shield would be no good, and the telescope would be inoperable or partially operable.
For the people here, I don't know the exact dimensions of a tennis court, but it's about, and keep in mind, this is someone who doesn't play tennis, so I'm sure someone online will correct me. It's about 2 of these white canopies you're sitting under. So, side by side. So, it's actually, that's massive. The scale just hit me. Anyway, was there a question out here? Perfect.
By the way, the sun shield is 22 meters by 12 meters for those who like precision.
Yes, you showed us a schematic of the Lagrange points.
Yeah.
One of those points, L4, where is that in relation to Earth?
L3.
Is on the exact opposite side of the sun. Yeah, it's the gravitational force of the two body system comes to null at these points. And remember, these points rotate, right? They revolve around the not rotate, they revolve around the sun. So the Earth and the whole system is moving like this. So L4, it's not a fixed point, it's a fixed relative point.
So it's basically you go out there and you're using the Earth as a counterbalance. Would that be mathematically what's going on?
The gravitational force of the two-body system comes to null at these points. And so if you were sitting out here, you would not feel the tug of the sun or the Earth as long as you were sitting here or here or here. And of course, this isn't drawn to scale. You know, this is a lot further out, that L2. Mm-hmm. This is L2.
It's doing
It's
donuts
just-
out in
it's just-
space.
It's just circling L2. I don't know exactly how big that orbit is. Yeah, and my guess is that maybe there might be too much junk right at the L2 spot. It's like an eddy. You know, the problem with having it at this point is that it's an eddy for anything.
Things like to sit in the calm areas of the stream. So it might be leading into the next online question. Does the James Webb have any defense against things like microparticles, particles, and things bigger? The rotation might be one of them.
It might be, but it's also the prayers of the astronomers, I guess, because as I said early on, it got hit by a microparticle. So it's dangerous. They're thinking that this is going to be operable for 5 years. They've already said that they use less energy parking it where it's at, and that it might extend the mission life. If we avoid those obstacles, we could probably get 10 or 20 years out of it.
All right. So our next question here.
Staying on that slide, L1. I believe you said that there was something out there that would give us a warning if a huge solar flare, solar storm was headed our direction.
Yeah, SOHO, it's called. It's a satellite. Absolutely. And you know, it's not the only warning. I mean, when that CME, the coronal mass ejection, happened, that gave us northern lights, we saw it at the solar observatory, saw it as it left the sun. So, you know, they could see it visually, but L1 is the first point where we could really measure the strength of those particles because we have an instrument there. We could see it visually, we could guess just how drastic it's going to be. So our warning is really, the first warning is really, once that ejection has left the sun, we see it, we can plot its course, and we have a good idea if it's going to hit us or not, or come close to us.
Yeah. As Earth does its revolution around the sun, does L1 stay in that point, or does it follow us?
It follows us. That whole all of those 5 Lagrange points follows the Earth because they are calculated and they exist because of the interaction between the sun and the Earth. So as the Earth moves, the location of those points move.
All right. So our next online question, actually, it was a comment, probably that you made about looking for things. The comment was, tools are only as smart as the people making and using them. So
Sometimes smarter.
So I think that was probably in response to that quote you had from the NASA director, where I want to know more about the things we don't know.
Yeah, the instruments provide us with data, and scientists try to interpret that data. Sometimes they're right, sometimes they're wrong. When you're doing science correctly, you're always taking your conclusions and looking at whether they hold under the new data that's available.
Was there another question out here? Keep in mind, I'm night blind, so if you don't raise your hand and wave it about, you're invisible. All right, so our next online question: do the rings around some planets make navigating around them with probes now, or maybe later crewed craft, or difficult, or are they something like the satellite paths around Earth that can be calculated out so they're not so much of a hazard?
No, they make navigation hazardous. Luckily, they're all thin, so you can fly over them and or under them. But there's a lot of little chunks of rocks and ice and all kinds of garbage that you wouldn't want to fly through, unless you want to fly through to measure what you're looking at.
All right, online people, get in those last minute questions if you have them. I see another question out here.
Good eyes.
So you said that Jupiter has Jupiter has rings, right?
Yeah.
If I've heard of like probes being sent out to explore Jupiter's moons, would the rings be hazardous to exploring the moons at all? Or are the moons farther away from Jupiter than the rings?
I don't
So
know.
are the moons in the rings?
Most of the moons are outside. I'm not sure about Io. Io's the closest one, and Io's interesting because it at any given time it has 1 to 200 volcanoes on it, and it spews up all this sulfur, and so it actually, a torus is like a donut, and so there's actually a torus around Jupiter of some of this sulfur coming out of Io. It's really interesting. You should Google it. But most of the moons are outside. They're probably all. I'm guessing Io is outside also, outside of the rings. And
But-
Jupiter's rings again, they're so thin. We had to fly a spacecraft by Jupiter just to see them.
I'm also certain that there's probably data out there where you can math out whether any of the moons are within the rings or not, because I'm sure someone somewhere has that data. Maybe not us, but someone does.
Yeah, Saturn has moon-like objects that I don't know if they call them shepherd moons or something, that are inside the rings, and they're responsible for some of the gravitational interactions there with the rings.
All right. Were there any more questions out here? Bueller. All right. And it looks like our online questions also ended. So I want to thank you all for joining us.
Yeah, thanks for coming
thank
out
you
in the rain.
again, Walt, for giving another great talk. And until next
you.
time, clearer skies and better seeing.
Oh, by the way, I've got some James Webb Space Telescope stickers that I got from NASA. If anybody wants them, I think I have them handy. Oh, my pleasure.